All right, let's get started. So first off, I think lecture, or at least lecture relevant to homework number 7, is going to be pretty short today because all we have to do is finish out that example 15, and then that's everything not only for homework 7 but for our second exam. So I am going to try and take care of that first, and then hopefully I think that will lead into a discussion on homework 7 if needed. What we'll do is we'll probably spend the remaining bit of time sort of introducing the next concept that'll be discussed after the exam, which is the concept of development length. Development length won't be on the second exam. It'll be on the final, but it's worth at least getting it kick-started. So just so everybody's clear on the timeline, we have exam 2 on Wednesday. So the homework is due Monday. The solution for that homework will immediately upload. So it's kind of tough to accept late submissions if you've got the answer. So I do need that in advance. We can talk when that's are on Monday. We'll do the same thing we've always done. I'll have an exam review session, let you all ask whatever questions you want, and then it's exam time on Wednesday. Sound good? The only other thing I would mention is on Monday, we're having our exam review. On Wednesday, we're having the exam. Friday, we're going to start development length, and just to give you a little bit of background, Marshall has a series of programs directed at trying to make us better teachers, and one of the programs is called a series of open classrooms. So what Marshall's done is they picked a series of classes for professors to come and visit. So for instance, Dr. Waite's doing a couple, and I'm doing one as well. I would have done steel as well, but that room's kind of packed, so getting extra people in there is a thing. Long story short is on Friday, I know I have somebody coming. So there'll be another professor here just hanging out, just checking out what we do in engineering. So who's that? So just let, you know, they're just going to hang out and learn about development length with us. So moving on. Moving on. All right. Sound good? Okay, so just to recap where we had left off, let's see. Way ahead. Okay, so we had discussed the idea of instantaneous deflections. So the idea behind instantaneous deflections are that you cannot compute live load deflections directly. Instead, you have to compute dead load deflections, and then deflections due to the presence of dead load and live load, and then you take the difference between the two. And so we had pretty much done that on the previous example, and we had gotten a live load deflection of, I believe it was something like 0.222 inches. Was that right? Did I get that right? Okay, so we had a dead load deflection of, and I think it was 0.245 inches. Then we had a dead plus live of, and I think it was 0.467 inches. And then the live load deflection was 0.222 inches. And we got that by taking the dead plus the live minus the dead. Am I correct on that? Okay. So, and that was fine for instantaneous deflections. And then we started the discussion of long-term deflections. And there's a couple of things that you need to keep in your head when you're talking about long-term deflections. Okay? The first thing that you need to keep into your head is that the deflections on day 1 and the deflections 10 years from now are not going to be the same. And they're not going to be the same because concrete properties are not the same on day 1 as they are 5, 10, 15, 20 years down the road. And there's a few reasons for that, but primarily it has to do with the fact that concrete properties are not static. They do slowly change over time. So typically what happens is your long-term deflections are larger than the deflections that you get on day 1. In other words, your long-term deflections are larger than your instantaneous deflections or your immediate deflections. So that's sort of the first thing that you got to keep in your head. The second thing you got to keep in your head is how much of that live load is sustained. And I wish there was a good, oh, if this is the structure, it's 30%, and if that's the structure, it's 80%. I wish there was a good answer for that. I wish that there was a straightforward, hey, here it is, plug and chug, that's the equation, or there's some table that'll tell you what it is. Unfortunately, there's not. It just boils down to judgment. An office building might only see 20% of its design live load all of the time, whereas a library or a storage facility might see all of it all of the time. So what we're ultimately going to be doing today for this next example is we're going to try and determine how much of that live load deflection is sustained. Now, just like with just a live load deflection, you cannot compute a sustained live load deflection directly. You have to compute dead plus sustained. So we're going to have two more deflections that we're going to need to compute. This one we're going to compute directly, and then this one we're going to compute by taking the difference between the dead plus the sustained minus the dead. So this one's going to be easy since we already have our dead load deflection. We're going to compute this one directly, and this one we're going to take the difference of. Now, the reason why we need that is because ultimately what we're going to do, I'm going to skip a couple slides, ultimately what we're going to do is this. We're going to compute a total long-term deflection. So our total long-term deflection is going to be a function of three things. First off, our immediate long-term deflection, our dead load deflection, but that's been modified by that long-term effect, but the time period is essentially infinity because the dead load doesn't go anywhere. It's there all the time. It's permanent. Plus, however much of that live load is sustained, and then we have to adjust that by the duration. Okay, and so this is going to be our fundamental formula for computing the long-term deflection effects. Okay, so what we'll need is we'll need our multipliers. We'll need our lambda values. They're pretty simple. Lambda is generally defined as a denominator of 1 plus 50 times rho prime, and the top is this time-dependent factor. That time-dependent factor just comes from this chart. We're going to interpret that here in a little bit. So one of the things to keep in mind with this chart, you can see as time increases, our time-dependent factor goes up. So what that's saying is that as that load sits on the beam longer and longer and longer, those deflections are going to increase. But you can also see how it plateaus. And so what do you think, what's the highest plateau value on that chart that we see? 2. So that's why when we look at dead loads and we have a modifier that's for an infinite time period, we still have our same denominator, but the top is 2. So to give you kind of an idea of how that's computed, it's a pretty straightforward process. Now, one other thing to point out, this rho prime, remember that rho prime is a reinforcement ratio. And rho prime is a function of whether or not you have compression steel, right? Remember, steel up top. Remember, we have a singly reinforced beam, which only has steel in the tensile region, but a doubly reinforced beam has steel not only in the tensile region, but in the compressive region as well. Okay, and if you remember, a while back I said that if you have a doubly reinforced beam, one of the benefits that you get is you have a benefit from long-term deflection performance. Well, why is that? Here's why. Because if you have reinforcement, a doubly reinforced beam, then you get a benefit here. Now, if you only have a beam like we have in example 15B, see there's no compression steel, right? It's just tensile steel. Then rho prime is just 0 because it's the ratio of how much steel you have to how much concrete you have, and there's no steel, so it's 0, right? Does that make sense? Okay. So ultimately, when it's all said and done and you're doing deflection calculations, you're ultimately after 2 values, okay, when it's all said and done. So, and I'm drawing on the board here because there's a couple images and values I want everybody to keep in their head. So ultimately, you're after 2 things. You're after the immediate live load deflection, and you're after the total deflection. Now, why do you care? Like, who cares about these? Who cares about this instantaneous deflection and this total deflection, taking into account long-term effects? Well, first off, just let's take care of the mechanics. We've already done this one. We did that one in example 15A. We're going to do this one in 15B. So don't worry, we'll go through it. But why do you care? Well, here's why you care. And let me see if I can blow this up a bit on the screen. So this is from ACI 318, and what this is doing is it's telling us what are our deflection limits. Okay. So what do I mean by that? Well, up until now, we haven't really looked at deflection limits, but we have looked at moment limits and shear limits. What do I mean by that? Let's take moment. Okay, so you all know how to compute a phi mn, right? Mn being the flexural capacity of that beam, how much that beam can hold up before it's going to fail, and then phi is our adjustment factor. That's our safety factor, if you will. So phi mn is sort of an adjusted capacity, whereas mu is an adjusted demand on that beam. You know, we're putting dead loads on the beam, we're putting live loads on the beam, and then we are factoring them accordingly. Sound good? So so what I mean by checks, as long as that phi mn value is greater than or equal to how much load we're putting on the beam, then we're good, right? That tells us that the beam is safe. And that's the question that we ask when we're looking at moments. And when we're looking at shears, we have something similar. We have phi Vn, then we compare that against Vu, okay? Well, with deflections, we're doing something different. These two values here are the actual deflection on the beam, okay? And what we're comparing that to is what's allowed, okay? So there are two deflection limits that consider immediate or instantaneous deflections, and then there are another two that consider long-term effects. So let's look at the two up top, the immediate deflections. So first off, we have a flat roof not supporting or attached to non-structural elements likely to be damaged, and then we have a floor element not supporting or attached to non-structural elements. So if you're doing an immediate live load deflection check, it depends on whether or not you're looking at a roof beam or a floor beam, okay? So if you're looking at a roof beam, we allow a little bit more deflection than we do a floor beam because more often than not, people aren't on the roof. So we're not talking about user comfort and user, like usability from a day-to-day performance standpoint. So we have a little bit more of a stringent limit on floor elements than we do roof elements, okay? So what I mean by stringent is if we're looking at a floor, its maximum deflection or beam deflection is L over 360, whereas for a roof member, it's L over 180. Does that make sense that the L over 360 is more stringent, that that's a tighter limit? If you take the length and divide it by 360, that's a smaller number than if you take the length and divide it by 180, okay? So L over 360 is a very, very common deflection limit for floor elements in buildings. So for bridges, for instance, a common deflection limit is L over 800. The loads are bigger, the geometry's bigger, it's a different story altogether. So for this problem, and you'll see how we handle this here in a second, we'll have to determine which deflection limit is appropriate for the problem that we're looking at. Now, the other two limits are going to be looking at delta total, the total long-term deflection limit. And the two categories are whether or not they're supporting elements that are likely to be damaged by large deflections or whether or not they're supporting elements that are not likely to be damaged by large deflections. And so if you remember, one of the things I mentioned last time was, do you remember me talking about plastered roofs? That if you have a plastered roof and the beams deflect too much, that you would crack the plaster? So that might be a floor beam that's connected to an element that's likely to be damaged by large deflections, and specifically attached to a non-structural element. The plaster is not holding the building up. The roof beams and the floor beams are, right? Whereas if it's attached to an element that's not likely to be damaged, maybe we can allow for a little bit more of a loose deflection limit. All right, does that make sense? All right, any questions? Okay, so let's look at example 15B. So just to give you all kind of an idea. So we're looking at, basically we're looking at example 15A. It's the same beam. And what we're trying to do is figure out what's going on with this beam in regards to whether or not it's going to meet long-term deflection limits and immediate deflection limits. So we're going to consider that this is a floor beam that is likely to be damaged by deflection. So what I say likely to be damaged, I mean it's attached to elements that are likely to be damaged. Also, we're going to consider that 30% of the live load is sustained over a period of 3 years. Okay? Everybody okay with that? Now, there's a few values that we've already computed, and I'm going to put them on this board here so that we don't have to rewrite everything from the last video because it's exactly the same as we did before. What was the cracking moment? Does anybody remember that from this beam? Because we had already done that. 27.39, and that was foot kips. We had a gross moment of inertia. I think that was 8,000. We had a cracked moment of inertia. That was a lot smaller. What was that? 4,067. And we had an E value. What was that? Anybody remember that? No. The moment or the modulus of elasticity. 3122 what? Okay. All right. So last time we had organized this in a big table. You can put this in the table. You can do it however you want. It really doesn't matter. Okay. So here's example 15B. Okay, so first off, we know that the live load deflection was 0.222 inches, and what we're after is the total deflection. Bless you. That's what we're after right now. So let's see if we can work that out. So we have a beam. How long is that beam? 20 feet. Now, let's look at the loads. Now, the way I'm going to draw this is this. We've got a load, and then we have a load on top of that. And so we're going to handle each of these one at a time. So the first one is the dead load. And how much load was that? Say it again. 1 kip per foot. And then how much was the live load for this problem? Like how much was it? It was 0.7 kips per foot. But actually right now, I really don't care about the live load because I've already figured out the deflection due to the live load. I already got it's right there. It's 0.222. So I don't really care about that. Instead, what I care about is how much of that live load is sustained. I care about the sustained live load. And tell me from this problem how much of that live load is sustained. Like not the calculation, but how much is sustained? 30%. So what I need is 30% of the live load. So that's 0.3 times, and what's the live load? You said 0.7? And so 3 times 7 is 21, so that's what, 0.21 kip per foot. Is everybody okay with that? Okay, so remember how this works. You know, we have to determine our applied moment to get an effective moment of inertia and an effective moment of inertia to get a deflection. So let's start off with our applied moment. Now what's generally the moment equation going to be for a simply supported beam with a uniformly distributed load? Like how do you calculate moments? WL squared over 8. So we need W. how do I compute W? What is the applied load going to be? It's going to be 1.21. We're not going to do 1.2 dead plus 1.6 live. We're just going to add them up. So that's WD plus WSL, and so that's 1.21 kip per foot. And so therefore, the applied moment is WL squared over 8, so 1.21 kip per foot, 20 foot squared, all divided by 8, and that comes out to be what? Say it again. 60.5? Do I have a second on that? Awesome. 60.5 foot kips. Okay. And so now that I have that MA, what do I do? IE, right? I compute an effective moment of inertia. Okay. An effective moment of inertia then, remember, it's the cracking moment divided by MA cubed times IG plus 1 minus that fraction cubed. Ooh, got away from me there. Times the cracked moment of inertia. So do I need to fill that in with all that data, or can you all do that? So we have MA is 60.5. The cracking moment is 27.39. This is 8,000, and that is 4067. Y'all think you can do that? I'll give y'all a second on this one. This is a big one. So you got 4431 point, say it again? So 4432.0, that'd be a fair statement. Now what are the units? It's a moment of inertia, so it's just inches to the fourth. Now do I have a second on that value? Awesome. Okay, so that's our moment of inertia, and then what do we do with that moment of inertia? We use that to compute what? The deflection. Now, what are we computing the deflection of? There you go. Exactly. The whole thing, the dead plus the sustained live load. And so that's 384 ECIE 5W L to the fourth. And again, remember, that equation only works because it's a simply supported beam and it's a uniformly distributed load. If you got a point load and you say, oh, that's a point load, I'm just going to divide it by 20 to kind of make it look like a distributed load so I can use that equation, bad. No good. All right. So 384, and that's 3122 KSI. Now the moment of inertia is what we computed up here, the 4432.0 inches to the fourth. 5, and then we have 1.21 kips per foot. And then this is 20 to the foot to the fourth. Am I missing anything? There we go. 1728 inches to the third divided by cubic feet. What do we got? Say it again. 0.315. 0.315 what? There we go. Okay, do I have a second on the value? Okay. So that means that this value right here, this dead plus sustained live, is 0.315 inches. Sound good? So if we want, we could actually go into this equation right here, and we could say, okay, that's 0.222 inches plus, we have some lambda that we haven't figured out, times this value is 0.245 plus some lambda value we haven't figured out times whatever this is. Now what is that? What is the sustained live load deflection? How do we determine that? There we go. I'm going to do a little bit better job there because that does not look like it did. And so what does that come out to be? .070 inches. Do I have a second on that? Everybody good? All right. Okay. So that means that this is 0.070 inches, and that means that this right here is 0.070 inches. So does everybody see how this deflection equation is working out? We have the live load deflection plus the dead load deflection modified by whatever this is, and then we have the sustained live load deflection modified by whatever this is, right? Probably a good idea to start figuring out whatever these are. Sound good? Now, let's go back to the beam, and let's make sure that we're clear on something. What is rho prime for this beam? 0. And why? Because there's no compression steel. So if this is 0 and that is 0, what is this? What are these lambda values going to come out to be? Whatever these are, right? Make sense? So would a fair statement be the following? That this one, what's this one going to be? 2. And this one is going to be whatever that modification factor is, right? Times 0.070 inches. Would you agree with that? Now, this is our time-dependent factor, right? But how are we looking that up? What information do we need from this problem in order to look up this value? 3 years. That's our duration, right? Now, how many months are in 3 years? 36 months, right? So let's do this. Oh, God. I knew that was going to happen. Okay. All right, let's see something. Let's see if I can draw a straight line here. Actually, let's do that. Let's do that. Okay, so we said what, 36 months? So 36 months, that's about right there, right? And so what we're trying to look for is that value right there. That'd be a fair statement? Now, typically what we do when we're looking at time-dependent factors is we look up and round to the nearest tenth. So what do you think we ought to do, 1.7 or 1.8? I'm thinking 0.8. So let's take this. Let's take that as 1.8. So therefore, since rho prime is 0, lambda for infinity is 2, and lambda for 3 years is 1.8. So therefore, delta total is delta L plus an infinite duration for our dead loads plus a 3-year duration. I don't want to say 3R, it's 3 years. A 3-year duration for our sustained live loads. So 0.222 plus 2 times 0.245 plus 1.8 times 0.070. And so what does that come out to be? Say it again. 838 inches. Do I have a second on that? So that's not too bad, right? That's a pretty simple calculation. So ultimately, when you're doing a deflection problem, you're after two things. The live load deflection, which is 222 in this case. This is 838. Now, those values by themselves really don't mean much because that's a deflection. I don't know whether or not that's an acceptable deflection. So let's check out each one of them independently. Okay? Now, in order to do that, what I'm going to do is I'm going to screen capture. Where's my snipping tool? This statement right here. Actually, let me just do the whole thing. And let's snip this. That way we're looking at the same thing and I don't have to keep going back and forth between slides. Okay, so we have two that are referencing the immediate deflection and two that are referencing the long term. So let's take the immediate. Which one are we going to be dealing with, the first one or the second one? What's the difference between the first and the second one? The first one deals with flat roof elements, and the second one deals with floor elements. Which one matters to us? It's a floor beam, right? So what we're basically saying is this, okay? Our live load deflection is 0.222 inches. What this table says is that our maximum live load deflection is L over 360. So that's what, 20 feet divided by 360. Does anybody have a problem with that calculation? We need to convert that to inches so we're comparing apples to apples. So we need to multiply this by 12. And so what does this come out to be? 0.67. Do I have a second on that? What does this mean? We're good, right? This beam responds appropriately under immediate live load deflections. Now let's look at total long-term deflections. So our total deflection is 0.838 inches. What is the maximum deflection? Is it L over 480 or is it L over 240? 480. Why 480? Likely to be damaged. So this floor beam is connected to elements likely to be damaged by long-term deflection. So this is L over 480. So that's 20 feet over 480 times 12 inches per foot. And what does that come out to be? .5. Do I have a second on that? What does that mean? It's not good. So does this beam meet adequate serviceable deflection requirements? No. Given the complexity of this problem, how would you fix it? I'm asking you. Make the beam shorter. That is an option, okay? Why would making the beam shorter help? It decreases your maximum moment, but it also decreases your maximum deflection. Remember, moment is a function of L squared, but deflection is a function of L to the 4th. So even if you decrease your deflection by or your length by a foot or two, that might make a big difference, okay? So that is one option. What's another option? Hold on. What'd you say? Put in some compression steel. There you go. If you put in some compression steel, you'd have a solution that works. So here's a couple options. So you know, we can write this down. You know, decrease L, add compression steel. What else? There's other options besides that. And what value do you think would affect it the most? Like, it's a rectangular beam, so you're either going to make it wider or deeper. What do you think is going to affect it the most? What's that? The depth. So deep in the beam. There is actually another option that has to do with the beam that we're not talking about. It actually does have an effect here more than it has with strength. Why would, that's right, but why would changing the FC prime help? What does FC prime affect in all of these calculations? Give you a clue, it's in the box. Actually, there's two things it affects. Cracking moment, and it affects E, right? Remember, E is 57,000 times squared of FC prime. You bump up your FC prime, you're bumping up your E. You bump up your E, your deflections are going to go down. Right? There's a few options here, you know, and this is a problem that you could very realistically face. So, larger FC prime. It depends. If you have a 40-foot beam, you could have two 20-foot beams and add another bay of columns. That's very possible. Now, decreasing it by a couple feet, it depends on it. Ultimately, it's whether or not the architect's going to say yes or no. Sometimes they'll say yes, sometimes they'll say no, which is why I put it up there, but it's not the only option I put up there. I'm just thinking from a mathematical parameter perspective, what all could affect it. You are making a good point, though, and ultimately it's whatever the architect says. There is one other option I can think of. What are deflections caused by? Loads. So what can we do with the loads? Now, how do you reduce the loads if you're designing a library and it's going to be a library? You can't go to the client and go, let's design a hospital, you know. Add more beams. So reduce your girder spacing. Reducing girder spacing is going to reduce the overall load on a given beam, which is ultimately going to decrease the load on the beam. Now, the downside is that means you're adding more beams, so it just depends. So I'll say decrease S. Okay. Any other questions? Mm-hmm. Yeah, we're talking about an interior beam in a building, so it's not exposed to the elements. Now, what you're talking about is, let me just say this, in the world of bridges, there's a whole host of other things that we have to consider beyond this that have to do with what you're talking about, like shrinkage changes and changes in humidity and relative humidity and all that. So, everybody good? Now, I do have one other thing I want to talk about, and this has really nothing to do with this example, but it has something to do with your homework. I want to pass this out, and you'll see what I mean here in a second. On your homework, you're being asked to, one of the problems is doubly reinforced, but there is one thing that we actually haven't talked about in here, and it's really not very difficult, but I just decided, you know what, instead of like spending 50 minutes on an example that really only has one big point to it, I said let's just do this one via handout to kind of make it a little faster. Okay, where did my marker go? I had a marker. Ah, there we go. Okay, let me show you something. And I think this will make sense. So first off, I just picked a random mean. I just made some random stuff up. On the second problem on the homework, you're required to compute the cracked moment of inertia for a doubly reinforced beam. We've never done that, okay? So it's really not any different to what we've done before. There is just one little catch, okay? So if I have a singly reinforced beam, you know, like this, right? Okay, what I do is I convert that to a beam that's like that. Then I have that lump of concrete down below, right? Now, what is the area of that box right there? Like, how wide is it? It's B wide, and it's X tall, right? So the area is BX. Would you agree with that? Now, and let me fill this in. Now, let's say you have a beam that's doubly reinforced. So you've got, this going on, right? Same deal. We're going to handle it one part at a time, right? So here's your neutral axis. Down below, that's everything in tension. All you're going to have is a lump of concrete that's NAS, right? Okay, so this is AS, this is AS prime. Now the concrete that's up here, what's the area of that concrete? This is B, this is X. Is the area BX? No, because there's going to be two little holes right there. Because that's not concrete, that's steel, right? So I propose that the area of that concrete is not BX, it's BX minus AS prime. And then on top of that, we have that steel turned into an equivalent lump of concrete that's NAS prime. So the way I propose that you do this is it really doesn't matter what order you do it in, but what I'm saying is this. I said that the total area of this box is B times X, but the area of this little rectangle is not NAS prime, it's NAS prime minus AS prime. Because if I don't do that, I'm double counting that area right there. Does that make sense? Everybody okay with that? So if you've accounted for that, the process is exactly the same. When I sum moments, I'm summing moments about this axis, and what do I have up top? I've got BX times that moment arm of X over 2. Now this one's new. I have the area of this block, so n minus 1 times AS prime times the moment arm. How far is it from this dashed line to that block? Well, it's X minus D prime, right? And that's got to equal this chunk times that moment arm d minus x. Once you've got that, just plug and chug your values. It's a quadratic equation just like any other. There's your x values. Only take the positive one, and it's I plus AD squared. The only thing is you have 3 rows now. You have the concrete, the tensile steel, and a new row for the compression steel. Plug and chug, and you get like 3977. It's really no different than what you did for a singly reinforced beam. The only difference is that n minus 1. So, and I wanted to explain why. Does that make sense? Right here. The area of the concrete is not B times X. The area of the concrete is BX minus those holes right there. So see what I'm saying? If I didn't have this, I would have BX and then I'd have a rectangle that's NAS prime, and I would be double counting that area. You see what I mean? Does everybody else see that? I get the feeling you don't see it. Okay. Can I erase this? All right, let's do it again. Do you agree that here's the box, and so the total area of that box is BS minus AS prime? Okay. Do you agree that the steel is going to have an area like that? Would you agree with that? Now add all that up. What do you get? The sum is BX plus NAS minus AS. Or factor. Pull an AS prime, and what do you get? That's all it is. It's just factoring. That's all it is. Does that make sense? Did that clear it up a little bit? It's just algebra. Everybody else good? Did anybody have any questions on the homework? Because I have a feeling that was probably a question. You're like, what? Oh, the homework that we haven't looked at? Acting like I don't know things about stuff. That should clear up a lot of things on the homework assignment. It really should. Because that's the one thing I'm pretty sure everybody was going to ask about. I was trying to think what else I was going to ask, but I can't really think of anything else, or anything else I was going to say. If that's it, that's all I got, everybody. Monday, exam review. Come prepared to ask questions. That's all I got. We'll see you in about 10 minutes.